So we have mentioned earlier that we have a cache memory, and this cache memory is basically something will be with a small area, for instance, and it will be much closer to the processor, meaning that it will have a faster access time. And this will be a lot useful for the processor since it can act or access the information in a fast way, and it can exchange the data easily with the cache memory, and it doesn't have to go all the way to the main memory to bring the stuff. It is the same exact concept that we mentioned with the disk that you have at your room, and with like any storage unit that it might be at the building or the apartments or so on. We mentioned at that time that the processor will go to the cache in a certain location. If I found whatever I need, then I hit, or meaning that I will just directly use the information that I found. If I didn't find what I supposed to have, I miss. And if I miss, I will go to the main memory and ask the cache to bring the information from the main memory. And as soon as it is ready in the cache memory, then I can use it as a processor. So that means that there is a data handling between the main memory and the cache memory. But the question that we need to ask ourselves is, how is this data handling mapped to each other? How I will know if I need a certain information from the cache, how I will know where it is allocated directly at the main memory. So there is a certain mapping scheme that we need basically to follow. Let's look at the problem differently. Suppose there is a compound. In that compound, there are several apartments that holds certain number of students. And in that compound or dorms, for instance, we have a parking lot. And unfortunately, because of the limitation of the space, we haven't been able to have a parking spots available for each student inside that particular dorms or compound. However, we luckily have the possibility to have a parking spot or slot for each apartment. But each apartment has multiple students who lived on that apartment, who are sharing the apartments with different rooms inside that apartment, which implicitly indicate that these students who lived in the same apartment will share one parking spot. The question is, how the students will know that any student that belongs to a certain apartment, where exactly the parking spot available to his or her apartment? How we would know that? There should be a certain particular mapping scheme that will direct the mapping between the student or the apartment and the spot location. Here also the same exact phenomena or problem, that we would like to know exactly if there is a certain location inside my cache, how I would know where is the exact location of this information inside my main memory. How I can find this information if I missed in the cache. Or if you would like to park, how you would know what or which of the parking spots is the one that is designed or assigned to your apartment. Given that there are multiple students sharing the same spot, so this means that as an office of the compound, if I went to a certain parking spot and I found a car, I should at least knew that this car belonged to that apartment. But we need to know not only this information, we need to make sure, of course, that that car belongs to that apartment, which belong to the same spot, But not only that, I would like a certain information which would tell me that this is that particular students in that particular apartment. Because there are, for instance, multiple students sharing the same apartments, which means they are sharing the same spot. But which car would be belongs to you, not the other students, for instance? With the same way, we need to think about that. So this means that the mapping in this case is many to one, multiple students to just one spot, because that multiple students belong to the same apartments and the same parking spots. It's many to one. How we are mapping the many students to the number of slots available. Here also the same things with the cache. The cache has a small number of locations. The main memory has multiple or has a large number of locations. We need to see how we would be able to map this low number of locations to the large number of locations inside my main memory. Of course, we need to follow a certain particular rule or scheme or formula that we can use in order to know the exact spot location. Since we have many to one, so this is what we call direct map, meaning that each of the apartments would be able to have just one location inside the whole parking spot. Just one, many to one. It's direct mapping between this apartment and that particular parking spot. So here is direct map. Each memory block is mapped exactly to one block in the cache. So each apartment mapped to exactly one parking spot inside my parking lot. That means that lots of memory blocks must share the same cache block, which is exactly the same things that multiple students would exactly share the same parking spot as we mentioned. How to know your parking spot? We said that please follow this formula. Memory block address modulo the number of blocks in the cache, then you will know exactly where to park. Let's look closely at that one. This is our cache. Which is the parking spot. We have from 0 all the way till 7. So we have 8 locations. 8 different locations. From 0 all the way to the 7, or 0, 0, 0, all to the way to 1, 1, 1. This is my cache. In the main memory, or all of the large number of students, I have it here beginning from 0, 0, 0, 0, 0, all the way till this one, which is 1, 1, 1, 1, 1. Suppose they are 32 locations, and that's why I need just 5 bits to write a number between 0 and 31. That's why I wrote this in 5 bits. And suppose that each of these memory locations is belonging actually to a student number. So you, when you lived in a certain particular apartment, you have a number. And you would like to know, as soon as you have that number, where is exactly your spot location. So you will take that number, you will put that number here, modulo the number of blocks in the cache or the number of available parking spots in my parking lot, and then you will get a number. You know that you have to park here. Let's apply this rule, but with the main memory and the cache. You as the students, you have here the gray color with this number, for instance, 0, 0, 0, 0, 1. So at the very end, your number is 1. So 1 modulo the number of blocks in the cache. We have here 8 locations. So 1 modulo 8. What is 1 modulo 8? Modulo means the remainder, correct? So 1 modulo 8 is 1. Can think of this 1 divided by 8. This is 0. So this is 0. 1 minus 0 is 1. So the remainder is 1. So you know now that your spot location is number 1. So you have to go to number 1 and park. How about another students have this number? What is that number? This number is 9. 9 modulo 8 is what? Is also 1. Because 9 divided by 8, and then the remainder would be 1. So that guy should also park in the same parking, or is sharing the same parking spot. How about that guy? That number, this is 17. 17 modulo 8 is also equal to 1. So that guy also could park in this particular spot. If you do the same for this, you will find that also can park in this place. So all of these locations or all of these students can park in that particular spot. And if you do the same with any of the numbers, let's suppose that we will have this number here is 5. 5 modulo 8, the remainder would be 5. So that basically that this would park here. If you will do the same with this, you will find that also it park here, the same is park here, and so on and so forth. It's many to one. Yes, multiple students are sharing the same spot. There is also another thing that I would like to pay your attention on, that if you look at the very first or lowest significant 3 bits, you will find that they always match their parking spot number. With this is 001. With this, 001, 001, 001, and so on and so forth. Interestingly, with the blue is 101, 101, 101, 101, and also this is 101. But why is that? Why we found that they usually share the very first 3 bits in all of these locations, in all of these same color, if you will. Because basically this is 8 locations, log the base 2 of 8 is equal to 3, and that's why you just need 3 bits to specify which is which, and that's why the very first 3 bits of all of these locations would be exactly the same. So that means if I will go to that spot, I already knew that this can be either that or that car or that car or that car. So I already knew this information. It can be any of these cars. But how I will know the exact one? So I know it can be one of these grays, but what's exactly the one that I'm looking for? Or what, or how I would know that this is in particular your car, not the car of the other students that sharing the same spot, since that all of you have the very first 3 numbers the same. You will be given a number. That number will just hang it on the mirror or in the car. The very 3 bits, the very first 3 bits, as soon as I will see 001, I will know that you belong to that particular spot and you are parking in the right place. Then it should be okay. You shouldn't get any fine. However, for instance, we might have another rule that, as an example, since many students are sharing the same spots, so there is a time limit. So I need to know, like, if this car has that time limit or not. So this means, or gives us an indication that we need a little bit of more information to be able to specify that this is your car, not the car of all of the other students, correct? If you look closely here at these numbers, you will find that the next 2 numbers of the number that they are sharing the same first 3 bits are different. Meaning these last 2 numbers are 0, 0. These last 2 numbers are 0, 1. Last 2 numbers are 1, 0. Here is 1, 1, and so on and so forth. So now with these next 2 numbers, I can actually specify each of these grays color. And this is what we refer to as a tag. So with the first 3 numbers, you already knew where is the spot number. With the next 2 numbers, you already knew who is exactly using that spot. The same with the blue. Then very first here is 0, 0. the very first, sorry, the very last, if you will, 0, 1, or the most significant 2 bits is 1, 0, sorry, and here 1, 1, and so on and so forth. So with these extra 2 bits, I have been able to define a particular certain students among all the other students that they are sharing the same exact spot. Okay, so this information is basically enough for us to know the location, the spot location, and who is using that particular spot location. But is this enough? It depends. Suppose that the office of that particular compound, they have decided that they would like to do some renovations, for instance. And for instance, that some of the parking spots are still not ready for parking yet because there is a renovation coming along or coming through. So that means that before you park, you need to check an extra information if you can park here or not. Although from your numbers, you already knew that this is the one that belongs to you. But you need to know another information if this is ready or not. Otherwise, it might harm your car or you might get a fine. Here is also the same. We are saying that, hey, to the processor, hey, you need to get more information in order to know that this in particular, although it is the same thing that you are looking for, that this is actually ready for you to use. And that's why we can add another bit, which we will call or we will refer to as validity bit. Meaning that if it is valid or not, that spot is valid for parking or not valid for parking. In our case, if this data that I found that belongs to the same thing that I am looking for is valid to use or not. For instance, I just restarted my computer. So I might have at the very beginning in the cache just rubbish. So although I might found the same exact address that I am looking for, but actually there was rubbish there. That's why it would be not valid initially or at the very beginning, for instance. So this is what we have here. We have tags and the valid bits. The tags is, as we have explained, just the extra bits or bit that we would need to specify a certain particular students from all the students that are sharing the same spot. And the valid bit, it will say it will indicate if this is valid or not. 1, for instance, would be present. 0 is not present, as an example. So here we can see this also with the animation, that here we have the cache, it's 8 locations. We have the main memory and we have one of the spots. So 1, 0, 0, 0, 1. And we would like to know the exact location. So we have just applied the same things. It's 1, 0, 0, 0, 1, modulo 8. You get the 0, 0, 1. And that's why that one belongs to the 0, 0, 1 location, as you can see here. It shows you here why we found that actually always the very first 3 bits are common, because basically if you would get the log, the base 2 of number 8 is equal to 3, and that's why you have the very first 3 bits, they are similar. We will go over this a lot in other examples and you will understand it a lot more, but this is just for you right now. If you found all of these numbers, you will find that 001, 001 is just the very first 3 bits are common in all of these spots, and they are sharing the same exact location. The same example with this bluish, that the very first 3 numbers belong to the same exact 3 numbers here in the cache, and they are also sharing the same location. However, as we mentioned, the very next 2 bits would not be the same among all of the blocks that have the same color. For instance, with this blue, the very first here is 0, 0, or the very last most significant 2 bits is 0, 0. Here is 0, 1, and then 1, 0, and then 1, 1. So with these extra 2 bits, you would be able to differentiate between one of these bluish among the others. The same is happening with the grays. Or also, if you have like a certain numbers that will be hanged in your car, with these last most significant bits, I should be able to specify that this is exactly you, not any of the students that sharing the same spot with you in this particular. So let's look at this example, for instance. So we have here a memory reference, 1031. So what is a memory reference? This is what the processor is looking for. I am as a processor, the processor is looking for 10111. And here is the cache. This is the cache. This is the cache. As you can see, this cache, we have 8 different locations. 1, 2, 3, 4, 5, 6, 7, 8 locations. And I would like to know if this, what I'm looking for, is inside my cache or not. The very first things to do is just look at the very first 3 numbers, or to take that numbers modulo 8 and see like what is that and look at that location. Either or, either go to that direction or the other direction, both are the same. And with actually both, you can use it either or, it would be the same. Here 111, you will go to 111. Yes, here's the location. I found something valid. Yes, it is valid. Yes, but there is extra information that I need to check. Is the tag is the same or not? My tag here is 10. The tag that is there is 10. Yes, hey, this is the information that I'm looking for. So I hit. Hit means that now I can use it and exchange the information with the cache memory. Please give me this information. Here is you explain exactly the same things. Here is the tag. The tag here is equal. So now it is correct that the word that I'm requested as a processor would be in the cache. Also, I have a valid data bit. So this means that all of the information that I need is satisfied. So this is actually whatever I'm looking for, and I hit. Let's take that example. I will look also at the very first 3 bits. Very first 3 bits is 000. Yes, I will go to index 000. Valid, yes. The tag here is 01, but the tag here is 10. So this means that it is not the one that I'm looking for, because they have different tags. So this means that I miss. And if I miss, what would be the consecutive, or what would be the consequences, or what would be the next step if I miss? If I miss, meaning that I didn't find whatever I am looking for. If I didn't find whatever I'm looking for in the cache, I have, of course, to bring it back from the main memory to the cache. If you didn't find whatever you would like to study on when you was at your desk, what you need to do is just walk and go to the storage unit to bring it back to the disk. Here is exactly the same. If you miss something, this means that it is not in the cache right now. Please go to the main memory, bring it, and copy it to the cache memory. And this is what would happen. They will remove this and then bring the one with the correct tag from the main memory. Let's take another example. So 111001. We will look at 101. Yes, 101 is here, correct. Oh, but this is not valid. So not valid, of course, that I can't use it. So I miss. And in this case, again, another option of missing the information inside my memory, my cache memory. So here, this is just the same example as we have just described in the animation. So we don't have to go over it one more time in this particular case. Let's take an example. Here it asked you that consider a cache with 64 blocks and a block size of 16 bytes. To what block number does address 1200 map? So I have here, instead of 8 particular blocks, and in the previous example, we have in each of the blocks just 1 byte. Now we have 64 blocks, and each of the block we have 16 different bytes. Let's try to imagine it that way. So here, we have, this is my cache. Instead of 8, I have from 0 all the way till 63. So I have 64 different slots. And each of the block, I have from 0 all the way till 15. So I have 16 different spots available. If you as the students have number given the number 1200, in which of these spots you will park? Given that each byte is a spot, as an example. But here we have 64 different blocks. Each of the blocks, we have 16 different slots. How we think about that? There are actually many different ways that we can think about that. So in another sense, when you think about that, you can think of each location like that. Here, you begin with 0, 1, 2, all the way till 15, and then 16, 17, 18, and so on. And I'm asking you, where is 1200? Or in another sense, 1200 is in which block? So here we have 16 bytes per block, and we need actually the address 1200. With this 1200, I can do 1200 divided by 16 just to floor it. It will give me 75. And if I have 75, I can just apply the same idea that I had earlier, which is 75 modulo 64 now. It gives me the 11, because now with this 75, I'm talking about the blocks. So I just transferred the way of the bytes to the blocks. So I have 75 modulo 64. It gives me the 11. Another idea that we can think of this as follows. It can be, for instance, 16 by 64. If you do that, it is 1024 different values, correct? So all the way till here, when you count this one, it's 0 all the way till 1023. So it is 1024 different locations. This is the first one, but since it is looping, wrap around, so we need to know 1200, where is exactly located in my second wrap, for instance. How to know that? It's just 1200 minus 1024. It will give you 176. So now we knew that 1200 in the second wrap is actually 176. So if you count from here, 16, 17, 18, blah, 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 and so on, you will find at a certain particular place 176. We need to know where is this 176. How we will know that is just 176 divided by the number of bytes or location inside the very first or each of the blocks. So it will be 176 divided by 16. It will give you 11. So actually it is in block 11, for instance, if this is block 11. So it is here. But this did not answer us which byte or which slot inside the block 11. Correct? It did not give us that answer. It just gave us that 176 is in that particular, or the 1200, in that particular block. It's 11, block 11. But is it the first spot? Is it the second spot? Is it the third spot? Is it the fourth spot? Is it the 16th spot or not? This did not answer that. Let's see a solution also from another point of view, which will give us all of the information that is basically needed in this case. So here it gives you that actually another way to think about that. Let's assume that we will write the 1200 in binary, as you can see from here. And think step by step in how we can do the allocation. First of all, we have here 16 different locations, correct? How many bits do I need to specify 16 different locations? It is log the base 2 to 16 is equal to 4 bits. Correct? So I just need 4 bits to specify a location among the 16th available slots. So that means that the very first 4 bits in that number will specify my byte location. This is byte location. Since it is 0, 0, 0, 0, so that means if this is block number 11, my location will be here. It's the very first one, the zeros one in that particular block. But with this information, I still didn't know that it is in block 11. I just mapped that 11 because I already knew that the solution is 11. How I will know number 11 from that particular binary number? I will ask myself the second question. How many bits do I need to specify 64 different locations or 64 different blocks? Again, we have here this block, 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 and so on till the very last one. So we have 64 different locations. Log to 64 is actually equal to 6 bits. So that means that the next 6 bits will give us some interesting information. 1, 2, 3, 4, 5, 6. If you read that number, this is basically, it will give you the block number, which by the way is number 11. So with this binary, when I read the very first 4 bits, I understood that it is in location number 0. And when I read the next 6 bits, I will understand that it is in block number 11. So it is basically in spot 0 in block number 11. Also, by the way, if you read the whole that number, it will give you 75, which you received from here. This kind of idea, it gives you a huge amount of information if you think about it in that way. So assuming that this number is written in 32 bits, as you can see here, the very first 4 bits is belonging to the byte offset. The next 6 bits is belonging to the block number. And then anything else which is belonging to the tag. So let's look at the same problem exactly, but from another point of view. And instead of just the memory and the blocks and the bytes, let's take an example from a real situation. Suppose that we have a hotel, and in that hotel we have number of floors, and in each floor we have number of rooms. So here we have our hotel. Suppose we have 10 floors from number 1 till 10 as an example. And suppose that in each of the floors we have 12 rooms. So from 1 till 12. And this number is in decimal. Okay? And we are, as a management of the hotel, we would like basically to give a room number for all of the rooms that basically available at our hotel, on the sense that as soon as I will give the number to the guest, we'll understand exactly where is the room location. Just for your reference, if I have 12, so this is 12 rooms multiplied by 10, so I have 120 rooms inside my hotel, correct? If I have 100 floors, so this means that I have 1200 and so on and so forth, correct? One way I could think about it is have rooming from 0, 1, 2, 3, 4, all the way to 120. But the problem with that how the guest will understand automatically without doing any mathematical calculations where is exactly the floor and the room that is belong to him or her. So we need to design it in a way that it would be very easy for the guest to specify the room number and the floor number, the management team. So we asked ourselves a couple of questions. First question is, how many floors do we have? We have 10 floors. How many rooms do we have? We have 12 rooms. So if we have 12 rooms, how many digits do we need to specify a room number? The maximum number is 12. So 12 means I need just 2 digits, yes? 10, 11, 12, all of these needs 2 digits. I can't write 10 or 11 or 12 in 1 digit. So I need at least 2 digits to specify the room number. Correct? How many floors do I have? 10. Again, I need another 2 digits to specify, given that I am beginning with 1, not from 0 to 9, given that I'm counting from 1 to 10. So again, I need 2 other digits to specify the floor number. So why not to have the very first 2 bits for room number and the next 2 bits for floor number? And for instance, if I gave this number to the, of course, it will be just one number, 10, 12. If I give you a key with 10, 12 number, you will understand automatically that your room is in 10th floor and it is room number 12. It is a lot better than giving you that your room is 120. Correct? Because 120, you need to do a little bit of more math. But 10, 12 is easy. If you are in the very first floor and it's still the same number, it's 0, 1, 12. So you will understand that this is the floor and this is the room. And by the way, this is a common way in all of the hotels for your reference. This is a common way in all of the hotels in your reference. So we have seen, since we are working with the decimal, that the very first 2 decimal or 2 digits are allocated to the room number, to the byte number. The next 2 bits are allocated to the floor number, the block number. And then instead of decimals, we have binary. And it is exactly the same things. Back to our first example, that we have from 0 all the way till 63. So we have a total of 64 blocks or 64 floors. And in each of these, we have from 0 all the way till 15. From here, 0 all the way to 15. So we have 16 different bytes, which is rooms, correct? The very first bits, it will be allocated for the room number, which is the byte number. How many? I have 16 bytes. From 0 to 15, but I'm not using decimal, so I can say that I only need 2 digits to specify the 15. I am talking about binary right now. And I need to see, if I would like to write 15 in binary, how many digits do I need? 4. Because basically from 0 to 15, so this means that I have 16 different locations. So log the base 2 of 16 is basically 4 bits. So 4 bits here. How about the next? The next is the floors. As we have here, the next for the floor, we have 64 different floors, 64 different blocks. Log to the base 2 of 64 is 6 bits. So this is block number. This is byte number, or this is room number, so you will not forget, and this is floor number. By analogy, it's exactly the same concept, and this is what we had earlier. Here is the same thing exactly. We mentioned that the very first 4 bits is the offset or the byte number. Which byte? Which room? The next 6 bits will specify the floor number, or what we call the index, or the block number. Anything else in that number, we will refer to that as the tag. In this case, it is 22 bits. If I'm using a 32 bits number. By analogy, in the other one, we have a room, we specified the room, but how to specify you as an example, as a guest? I might need another information. Let's suppose that we will add a date. In that case, the date will be my tag, because I will know that there is a person or someone who lived in this particular floor, in this particular room, but on that particular date. Then I would be able to specify you among all the other guests that basically were in that same location. Here is exactly the same. That you can share the same exact memory, but in order to identify you, I need to have a little bit of more information. Instead of the date, this is what we will refer to as the tag. With the same concept as we had earlier with the structure hazards for the main memory, we have the same issue here with the cache memory, meaning that we have actually to separate the instruction cache memory from the data cache memory. It's just a structure hazard. Structure hazard happened when two different entities, for instance, would like to use the same exact place at the same exact time. Then there is a structure hazard. There is a collision, if you will. Correct? That's why, in order to avoid the structure hazard, please separate the data memory from the instruction memory. As you can see, they are actually would like to be accessed the exact same cycle. If they are exactly the same, then we will have structure hazards. But if we will have this as a data and this as an instruction, then we will avoid that. Now let's take an example of how actually we can do the direct map in this particular case. Here is my cache. I have 4 slots, 0, 0, 0, 1, 1, 0, 1, 1, and I'm expecting that I need only 2 bits to specify 4 different locations. And I will add here my tag for each of the locations. But all of this is my cache. And the processor is asking for all of these numbers, one after the others, and would like to see if these addresses are available in my cache or not. And we'll go over each of these ones step by step to see how the processor will act in a particular case like that particular example. First of all, again, this is my cache. My cache here, instead of having 8 different locations with as the first example, we have only 4 different locations, only 4 different locations. So instead of having the very first 3 bits that will be common, here we have log the base 2 of 4. So this means that it is 2 bits that would be common instead of 3 bits. Meaning that if there are numbers that sharing the same exact locations, they will share the very first 2 numbers, as we will see shortly. First of all, let's try to write these numbers in binary. So the 0 will be 0, 0, 0, 0. The 1 will be 0, 0, 0, 1. The 2 will be 0, 0, 1, 0. The 3 will be 0, 0, 1, 1. The 4 will be 0, 1, 0, 0. The 3 and 4 already written. The 5 will be 1, 1, 1, 1. Correct? Just in binary. And the processor would like now to access word reference 0, for instance. Or I need a reference 0 in this particular example. As we mentioned, 4 locations. And in each of these locations, we have just one particular addressable location. So with this very first one, I can do the same exact thing, that 0 modulo 4, and then it will give me 0. So I should look at address 0, and then if the 0 is there or not, I miss. If it is not, I miss. If I found it, I hit. This is one way to find the location. But there is also another way to find the location by looking at the very first 2 numbers. The very first 2 number here is 0, 0. So I will go to 0, 0 to see if my memory of 0 is located there or not. Unfortunately, when I look at that location, I didn't find that there is anything there because initially it is empty. Nothing in this valid, for instance. So that means that I miss. And when I miss, I have actually to bring the memory of 0 to my cache and add it here and just add also the tag of the memory of 0, as you can see from here. So as we mentioned, you need to know, or you can know the exact location of the 0 by two ways. Either by 0 modulo 4, 0 modulo 4 will give me 0, or by just looking at the very first two bits, which is 0, 0, you will know that this is the location as we mentioned here. Also, another information I would like to highlight that this is exactly the same cache memory, meaning that this one is a cache memory and this one is the exact cache memory. I'm just taking a snapshot of the same cache with time. So it is exactly the same. I just would like to see the process step by step, and that's why we drew it here different blocks or different snapshots of the same cache as you mentioned, as we already shown here. So with this, so this is, if we copy, this would be memory of 0. It is already copied here. And then the process is asking about the 1. The processor will go at the 1 modulo 4 would be 1, or the other way that this is 0, 1. So I will look at address 0, 1. When I look here, I didn't find anything. So it's basically I miss, as I missed also here. What I do when I miss, I will go and copy memory of 1. And then write my tag. It is 0, 0. And this will be the case. Just copy whatever, everything that I have here, I had here to here. So memory of 0, memory of 1, and this is 0, 0, 0, 0. And now I'm asking for 2. When I look for 2 modulo 4 is 2, or I can just look at the 1, 0. So 1, 0 location is here. I look at this one. I didn't find any information, so I miss. So this is memory of 2. And I will just add the 0, 0, so the 0, 0 will be here. Again, copy everything that I had here to here, because this is just a snapshot with time. Now I'm looking for 3. 3 means 3 modulo 4, or I can do the very last or very first 2 bits. This is 1, 1. So basically, I'm looking here. I didn't find, so I miss memory of 3. And again, copy with this one, the tag, so it is 0, 0. Copy everything the same here, memory of 0, memory of 1, memory of 2, memory of 3. Tags here are all 0, 0. Now I am looking for 4. But 4 modulo 4 is 0. Or if you look at the very first 2 bits, it's 0, 0. So actually, I should look here. When I look here, I didn't find that I have memory of 4. I found that I have memory of 0. So again, I miss. What I need to do is what? Remove memory of 0, copy memory of 4 from the cache memory, from the main memory, and just overwrite the information that I have here with the new tag. So copy everything that I had here right now. So it is memory of 4, memory of 1, memory of 2, memory of 3, this tag 0, 1, these are 0, 0. Now I need 3. Interestingly, I will look at the 3. It is 1, 1, 1, 1. I found that here, so I hit. So I don't have to do anything. It is there. I found it, so please use it. Copy everything that I had previously, because this is just a another snapshot. And now I need 4. Oh, I will look at 4. I will go to the same spot as before. I found that it is here, so I hit. Copy everything again. I would like at this point 15. So I will go to the very last 2 bits. It is 1, 1. Unfortunately, I didn't find 15. So I miss. What I need to do is just remove that and overwrite, of course, with memory of 15. The overwrite the tag with 1, 1, because the tag here is 1, 1. I can also know this information by 15 modulo 4, and 15 modulo 4 will give you that particular location as well. So this is here just shows you exactly what we have mentioned. One more things I would like to highlight here, that with all of these, we have 8 requests. 1, 2, 3, 4, 5, 6, 7, 8 requests. Among the 8 requests, we have 6 misses and we have 2 hits. So among the 8 requests, 6 misses and 2 hits, that particular example. Let's take another example here. Suppose that my cache right now is this. Here will be written the data. Here is the tag. Here is the valid, as we have mentioned earlier. And in this cache, we have from 0 all the way to 1023. So we have here 1024 floors, if you will. In each of the floor, we have 32 bits. But we already knew that we are byte addressable. So I need to know how many bytes do I have if I have 32 bits. 32 divided by 8, so I have 4 bytes, correct? So this means that this is 1, 2, 3, 4 locations. So that means, according to the hotel example, that we have 1024 floors, and in each of the floor, I have 4 rooms. How to address these things with the same exact concept. 4 rooms, how many bits do I need to address the 4 rooms? 0, 0, 0, 1, 1, 0, 1, 1. So I have only 2 bits. That's why the very first 2 bits here will be as a byte or room address, or byte addressables, or byte offset. So I will know that this is the room, or this, or this, or that. How many bits do I need for the floor? Is 1024. So log 2 to the 1024. It's basically equal to 10. And that's why here we have the next 10 bits to specify the floor number. Anything after that is just the tag. The tag will specify, as an example, the date that you had, for instance, to access that hotel, to access that particular floor number and that particular room number in that particular floor. So anything extra than the information that is needed to specify your location, I will assume that all of this would be the tag, and this will differentiate between you and the other guests who already use the same exact location, which location means floor and room number. Let's take another example. Here, with this cache, I have from 0 all the way to 255. So I have 256 different floors or different blocks. But here they mentioned that it is multi-word block. So just the previous example, I have 1 word, which is 32 bits. Here I have multi of these, multi-words. In that particular example, I have 1, 2, 3, 4 words. So these 4 words. In each of the words, I have 32 bits, but it is byte addressable. Again, byte addressable. So if it is byte addressable, I have to specify how many bytes do I have. In each of the word, I have 4. 1, 2, 3, 4. How many bits do I need to specify a room number? In 1 word, again, 2 bits. So the very first 2 bits will be used to specify a certain room number inside one of the words. Then go a little bit up by 1 level. How many bits do I need to specify, do I need to get in order to specify that which word should I use? I have 4 different words. 4 different words that, again, I need just 2 bits to specify which word do I have. So this will be byte number. This will be word number. So now I have specified the word and I have specified the byte. How many bits do I need to specify which floor or which block? Log base 2 to 256 is just equal to 8, and that's why the next one which shows you the block number. Anything after that will be the tag, and in this case will be the 20, because 32 minus 2 minus another 2 minus 8 then will give you the 20. You can think of this with the hotel example, for instance, that instead of having just one building, you have multiple of buildings. So you have 4 different buildings. You have north, you have south, you have east, you have west. So in order to specify a room number, you need to give one more information, which, as an example, if it is north or south, which building, either building number or a building direction. So I can give you also 1012, but 1012 where? Is it 1012 north or 1012 east or 1012 west, and so on? Or I might add numbers in the middle to specify that this is actually that direction, and so on and so forth. So I might write 10 and then north and then 12. Or this north, I can remove it and put another number to specify that this is actually one of the 4 locations. So I might say the very first 2 will be for the floor, and the next number will be for the direction, and then the very last 2 numbers will be for the room number. So if I give you 10, 4, 12, 10 means floor number 10, 4 means building number 4, 12 means room number 12. Here is exactly the same. I'm giving you here 2 to specify if you are here or here or here or here, but I didn't give you if you are here or here or here in that building. The next 2 numbers will specify in which of these wards you are basically allocated. And after you already knew this information, I will give you the next 8 bits to specify actually if you are in this floor, or you are in this floor, or if you are any of the other floors, and so on and so forth.